Good morning, everybody. The outline of the talk is as follows. First, what is an ADC? Then I'll go over some prior art. Then I'll talk about the continuous time pipelined analog to digital converter, which is a new way of combining anti-aliasing filtering with analog to digital conversion. And I'll summarize and conclude. So, our world is analog, as you all know, and analog signals are continuous both in time and value, but DSPs can only process signals that are discrete in time and value, and therefore, you need some interface electronics which takes a signal which is continuous in time and value and convert it into a digital signal. And that is the role played by analog to digital conversion. So, the basic idea is the following. This is continuous in time and value. The first step is to discretize time. So, you do that by sampling. So, now you have discrete time, but continuous values, and then you quantize this discrete time sequence to get a sequence which is both discrete in time and value. And since there are discrete number of levels at the output of this quantizer, you can encode it and get a digital output. So, this is what an A to D converter does. So, sample, quantize and encode, not necessarily in this order. It is straightforward to see that if I quantized first and sampled later, that will still work. And there are many clever ways of combining the order and the way you do quantization and sampling to get an implementation which is power efficient. So, a quick review of sampling. Well, the basic idea is that a slow signal can be recovered from its samples. It is straightforward to see that the signal, the continuous time signal that corresponds to these samples is the one shown in red. This is given mathematical form by the Nyquist sampling theorem, which states that the sampling rate must be greater than twice the signal bandwidth for us to be able to recover the signal from its samples. And all of you have seen this in your basic courses. So, that brings us to the first abbreviation of the day. It turns out, as we will see going forward, that even though Nyquist told us that you just need to sample a signal at twice the signal bandwidth, it turns out that in practice people actually use a sampling rate which is higher. Okay? And the ratio of the actual sampling rate to the Nyquist rate, which is the minimum rate needed, is called the oversampling ratio or the OSR. The next step is quantization, and quantization is simply taking a sampled sequence with continuous levels and converting it into one with discrete levels. It is a nonlinear memoryless operation. It is like rounding off a number to a nearest integer if you want, and since the output V has got a discrete number of levels, it can be represented in digital form. As you can imagine, if you round off a sequence, clearly you have lost information. So, there is some error which is called the quantization error, and the quantization error is less than half the step size and magnitude. Now, we are having hard enough time worrying about circuits which are linear. The moment you see characteristics like this, you can see that the math is too messy to handle. And when the going gets tough, engineers start to make approximations, and these are the approximations that are made in practice. The quantization noise, it is assumed to be noise, though it is not, because clearly if you know Y, you know V, and if you know Y and V, you know E. So, it is not noise at all, it is deterministic. It is assumed to be independent of Y. This noise is also assumed to be uniformly distributed over one step size. And having made 3 wrong assumptions, it doesn't hurt to make one more, which is that the quantization noise sequence is white. So, that is that's quantization. So, coming back to sampling, there is a fundamental problem in the sense that if you take a sinusoidal tone at a frequency b hertz and sample it at Fs, which is 1 over Ts, this is the sequence that you get. Unfortunately, if you take a sine wave which is Fs plus b and sample it at Fs, you still get the same output sequence. So, a tone at B and a tone at Fs plus B yield the same sequence after sampling. So, looking at the samples, you are no longer able to figure out what the input to the A to D converter was, and this is the well known phenomenon of aliasing. So, therefore, what do you do to fix the problem? You a tone at B, Fs plus B aliases to B, a tone at Fs minus B aliases to minus B. So, the baseband signal which you want to digitize has a content from minus B to plus B, and these bands in gray are the so called alias bands, which are frequencies from which will alias to baseband after sampling. So, what do you do to fix this problem? As you learnt in your introductory signal processing class, you have to put a filter which eliminates signals that can potentially alias into the signal band. So, though now you see why Nyquist is okay in the textbook, but not in practice. The sampling rate, if it is chosen to be exactly equal to the Nyquist rate, this so called anti-alias filter must have a response which is brick wall, right. And anything in nature which falls off suddenly is impossible. The only thing you can do is you can make an approximation which approximates this brick wall, and so what is done in practice is you oversample. So, in other words, you sample at a rate which is higher than Nyquist, and what do you gain? Well, if you sample at thrice this signal bandwidth, then the characteristic needed of the filter is relaxed from the brick wall, and as you keep increasing the sampling rate, the filter becomes easier and easier to do. And that is captured in this picture. I mean, there are various ways of approximating the brick wall. The Butterworth is just one of them. It's just jargon. If you have not seen it before, don't worry about it. All that this picture is telling us is that as the sampling rate approaches Nyquist, the order needed for the filter keeps blowing up. You can see that with an oversampling ratio of 2, in this case, you need a filter which is of 10th order. So, to summarize, if you have a small oversampling ratio, that basically means that you are sampling at a rate which is close to what is recommended by Nyquist. Designing the sampler and the quantizer is easy because the sampling instant, the time period of sampling is small, is large. You have a lot of time between samples so that you can process. But the filter design becomes very difficult. On the other hand, if you oversample, which is sample at a rate much higher than that recommended by Nyquist, then the filter design becomes easy, but sampling becomes difficult because you are oversampling. In many cases where you have very wide band inputs, right, technology limitations basically mean that you cannot afford to sample at a rate much higher than Nyquist, right. Maybe you can only sample at twice the Nyquist rate, thrice the Nyquist rate, something like that. So, ideally we would like to sample at a much higher rate, but technology limitations, transistor speeds prevent us from doing a good job at high frequencies. So, the signal chain, this is a very conventional signal chain which is in very wide use. You have an anti-alias filter, we already discussed why it is needed, and then you have an A to D converter. These converters operate at an oversampling ratio which is a little bit over Nyquist, and such ADCs are called Nyquist rate converters, are also called discrete time ADCs simply because they take the sample here and quantize it. So, they operate on a sample by sample basis. So, let us take a look at what the problems here are. And in passing I will mention that filter design is is a classical field. People have been working on filters for 40-50 years now, and every dB of SNR that can be eked out of a filter has probably been done. And likewise with ADCs, people are continuously improving on ADCs. A lot of the improvement comes from technology, and so these blocks have been individually optimized so far by a lot of researchers working over a lot of years, right. It turns out, somewhat surprisingly, that combining the filtering and analog to digital conversion into one animal, it turns out that gives you an order of magnitude improvement in performance. Performance meaning participation to get a given resolution. Okay. So, that is what I will be talking about going forward. So, before that, let me talk about what the problems are with this signal chain. So, the ADC itself, discrete time ADCs, the basic principle is you first sample the input, you need to store the input somewhere, and that's typically done on a capacitor. And then you look at the capacitor voltage and sample it and quantize it. So, the front end of a discrete time analog to digital converter typically looks like this. This is the capacitor on which the input voltage is sampled, and so during a sampling phase, this switch is closed, so the input voltage is sitting on the capacitor, and the moment the sample signal goes down, the switch is opened, and therefore, the input voltage is captured or stored on the capacitor, where it is then processed in the processing phase, and then you reset it and get ready for the next conversion. Now, when you take a capacitor which is initially uncharged and connect it to a voltage source, you have seen in your basic circuits class that it will ideally draw an impulse of current. But in practice, because of finite switch resistance, that impulse will become an exponential spike. Now, any active, those of you who worked with transistors know that if you want to, be able to supply a sharp spike of current, a sharp spike of a large amount of current, the quiescent current of the transistors has to be very large, otherwise there will be a lot of distortion. So, in other words, the person driving this ADC will have a very difficult time being able to supply these sharp spikes of current, and so what is done is to put a buffer in front of the sampler like this. The job of this buffer is to be able to supply these large spikes of current without distorting the signal V in of t. And it turns out that as we just discussed, typically this buffer will have a lot of current comparable to maybe 50% of the ADC's power, and it adds noise. All active circuitry adds noise and also distorts the signal, because this is made with transistors. Transistors are nonlinear and you get distortion. So, to summarize, the input load of a classic discrete time Nyquist converter has a switch capacitor in its front end, which needs a high power on chip buffer to be able to drive these spikes of current without distorting the signal. And typically these also use a much larger supply voltage, and they add noise and distortion. Now, so there are other challenges which I am not getting into, but they're all, again, these have been, this is a multi-billion-dollar industry and like many smart people working on it. So, a lot of these problems have been solved, and all of these involve extensive digital calibration, because a lot of digital logic you can now put on chip for very little cost. So, so this is the, so you need the filter for anti-aliasing, you need a buffer to drive the ADC, and this is the ADC itself. And remember that there is a steep trade-off between the order needed of the filter and the oversampling ratio, which is the ratio of the sampling rate to the Nyquist rate. Now, before I go forward, let me give you some jargon. A second order transfer function like this is often called a biquad. This is called a biquadratic section and is shortened as biquad. And what I would like to draw your attention to is that the high frequency roll off of this second order transfer function is, because 2 poles, it's 40 dB per decade. Now, how do you build a very high order filter? Well, you take many second order sections and cascade them. Now, all these second order sections are built with op amps and resistors and capacitors, and all of them also add noise. So, as you keep cascading these filter sections, you also keep picking up more and more noise, which is internally generated by each one of these biquads. So, as you keep increasing the order, so from 1 to 2 to 3 biquads, as expected, you can see that the frequency response dives down at a much rapid rate, 20 dB per, 40 dB per decade, 80 dB per decade, 120 dB per decade. And also, as you keep cascading more and more biquads, because each one of these biquads is adding noise, if you look at the noise spectral density at the output of the filter, you will find that when you go from 1 to 2 to 3, the noise spectral density keeps increasing as you keep adding more and more biquads. This makes sense, right? So, now let's come and before I go further, let me give you a quick primer on a fundamental noise power trade-off. So, let's say you have a filter with a transfer function h of s and it produces some noise. This consumes some power p, and let's denote the mean square noise as v square of n1. Now, if I take two identical filters, copy paste and short the outputs like this, what happens? The transfer function remains, I mean this is the Thevenin equivalent of this filter, this is the Thevenin equivalent of the lower guy. When I short these two nodes, just simply using superposition, you know that the transfer function is still h of s. The power dissipation is twice that of each, you have two instances, so the power dissipation is 2 times p. And what about the noise? Well, again using superposition, you know that if this is Vn1 and this is Vn2, the equivalent voltage, noise voltage here is half of Vn1 plus half of Vn2. So, the mean square noise Vn1 and Vn2 are being generated in two independent circuits. So, they are independent noise sources. So, the mean square value of the noise when you take two identical circuits and just plop them together is 1/2 the noise that you had earlier. The power dissipation is twice p. So, the key takeaway therefore is that if you want to reduce noise in a circuit by a factor of 2, you need to burn twice the power. And this is a fundamental thermodynamic limit. This has got nothing to do with the fact that you are a lousy designer, right? Okay. Now, therefore, taking this further, if you want to reduce noise by a factor of n, then you need to burn n times the power dissipation. So, with that background, let us say for a single biquad, the noise is x, the power dissipation is p, the area is A, the area of the biquad, meaning when you lay it out on an IC, you have capacitors which occupy space, you have transistors which occupy space, and it turns out that most of the space is occupied by the capacitors. And the roll off is 40 dB per decade. Now, if I cascade n biquads, the roll off at high frequency, I get a much sharper filter as expected, 40 n dB per decade. But let us say I want a high order roll off, but I want the same noise as a single section, right? Because I want to figure out what is it that's costing me what am I paying to be able to get this very sharp cutoff at high frequency. So, if I need the same noise at the output of n biquads, remember each biquad is adding its own noise. The noise of each of these biquads has to be lower by a factor of n, so that when you cascade n of them, you get the same noise as a single section. And just now, as we discussed, to reduce the noise of a biquad by a factor of n, we have a thermodynamic limitation. The power dissipation has to be increased by a factor of n. So, what is the total power dissipation when you cascade n biquads? So, as to get the same noise as a single biquad, you have n biquads, each one of them consuming n times the power. So, the total power dissipation goes up by a factor of n square, right. And likewise, with area, it turns out that if you, as we just saw, to reduce noise by a factor of 2, we had to put two instances of the biquad together, which therefore means that the area has gone up by a factor of 2. So, if you want to reduce the noise by a factor of n, you would have to put n instances together, which means that the area of each biquad would have gone up by a factor of n. You have n of these biquads. So, the filter becomes n square times larger. So, to summarize, for the same noise, if you want to build a sharper filter, it is actually very expensive to do so. You will be burning n square times the power and consuming n square times the area. And so let us get back to the signal chain. This is our ADC. This is the buffer needed to drive the ADC, because this guy is drawing spikes of current. and the anti-alias filter adds noise and distortion. And the sharper the filter you want to make, and why do you want a sharper filter? If you could make a very sharp filter, then you could reduce the sampling rate of the ADC and make the life of the ADC designer easy. So, a sharper filter means more power, more noise and more distortion, as we just saw. And the obvious question now is that, is there a better way to realize the same functionality, right? So, I hope the problem is clear. It turns out that there is, and the idea is what is called the continuous time pipelined analog to digital converter, which is a way of combining filtering and analog to digital conversion in one unit. Let me quickly go over the details. So, U of t is the input that you want to digitize. ADC 1 and DAC 1 form a coarse quantizer. So, V1 is actually a digital sequence, and V1 of t is an analog waveform, which is basically dependent on this digital sequence V1. So, V1 of t is basically a digital approximation of the input waveform. The difference between the input waveform and the approximation is the so-called residue. And you might be wondering, this is a delay line of delay Td, and you might be wondering what that delay line is doing there. It turns out, as we will see going forward, that this residue should be made as small as possible. It is advantageous to do that, as we will see going forward. So, to see why you need the delay, let us assume that this U of t is a very slowly varying ramp signal as shown in black, and V1 of t is a digital approximation. So, it is a staircase waveform like that. The difference between U of t and its approximation is this sawtooth like waveform, as you can see there. Even visually, it is apparent that V1 of t is a delayed version of U of t. So, you can make the approximation better, or you can reduce the residue by simply delaying U of t by half a clock cycle, right. So, if you delayed U of t as seen in black, the peak to peak residue goes down by a factor of 2, right. So, in other words, the delayed version is a much better approximation to V1 of t than the input itself. So, the key takeaway is that if you want to keep this residue small, the delay in this path and the delay in this path must be the same. And that intuition, of course, is borne out when you take a much faster signal. For example, this is a sine wave, and this is the input, and this is the digital approximation to the input. The residue is the one shown in red. If, on the other hand, I used a delay line with half a clock cycle delay, you can see that the residue is reduced significantly. The next step is to take this residue, go through what is called a residue amplifying filter. Remember, we are trying to make a filter and ADC into one. So, this is a filter H of S, and because the residue is small, you can actually amplify the signal without saturation. So, this gain G can be chosen to be large if this residue is made small. So, at this point, this G is just a number. It's it turns out that it's greater than 1, and this amplifies the residue, and the output of this residue amplifying filter is sampled by an ADC at the back. Now, let us take a look at what that sequence is. So, this is completely linear, and therefore, you can just simply use superposition. It consists of 3 parts. One is the input U getting delayed, getting gained up by G, filtered by this filter with an impulse response H of t, this is convolution, and sampled at n times Ts. That is one contribution to VB. The other contribution is this sequence V1, which goes through G, H, and gets sampled. And if you look at this yellow block here, you can see that this is a discrete time sequence. This is also a discrete time sequence. In the middle, you have a linear system, and therefore, you can always find a digital filter that relates the input sequence to the output sequence, right. So, those of you who have taken a DSP class, this is the same as what's called the impulse invariance transform, if that rings a bell. Okay. So, the bottom line is that you can always relate the contribution of V1 to the output through a digital filter, which I call H of n. And that of course, finally, this is the quantization noise of the back-end ADC, which is this. Now, this is a digital signal, this is a digital filter, so this is a digital quantity. Likewise, the back-end ADC's output is also a digital quantity, and you can kind of fool around the equations, and basically, you finally end up with this. I'll give you the intuition going forward, but what this is telling us is that this is the filtered input and sampled. This is the quantization noise of the back-end ADC divided by G, and this is telling you, what this equation is telling you in words is that the filtered input after quantization can be recovered by computing this, which is the back-end ADC plus the output of the first stage convolved with the equivalent digital filter of the analog part. So, this is basically the complete analog to digital converter, which now combines filtering and analog to digital conversion. That is the digital reconstruction engine. So, that is V1, this is a digital filter, and you add it to the output of the back-end ADC and divide the whole thing by G, just like our math said, and this is the output of the continuous time pipeline. And as you can see, again, this is the input delayed, filtered and sampled. This is the quantization noise. So, the analog filtered input plus the quantization noise is equal to the digital output. So, it is an anti-alias filter plus an ADC rolled into one. Now, some intuition. This is the input to be digitized. This is the digital approximation to the input, and therefore, the output at the back has the filtered input minus the filtered approximate input plus quantization noise. Now, the approximate input is also available digitally here, and therefore, when you add this to that, the filtered approximate input goes away, and what you get is the filtered input plus the quantization noise. Anyway, so now once you get this concept, it is straightforward, as you can imagine, to extend it to multiple stages. So, here is an example of a so-called two-stage pipeline, a continuous time pipeline. The idea is that you copy paste, and then you have a digital filter which cancels out the effect of this residue, and similarly another digital filter which goes and basically reconstructs through V2. And once you understood the previous one, this is pretty straightforward. But the key point now is that the input, as you can see, and which will also be evident from the math if you go through it, but intuitively you can see that the input goes through two stages of filtering before getting sampled. So, you are getting high order anti-alias filtering. Most importantly, each stage now has a gain, right, and therefore, the noise and distortion of each of these stages is reduced by a factor of, so for example, if noise is being produced here, that gets attenuated by a factor of 16, but there is a gain of 4. So, basically noise power wise you get a factor of 16 advantage, and because this is 1/16 here, the step size of the back-end ADC, the quantization noise added by the back-end ADC also gets reduced by a factor of 16, and consequently you can use a much poorer ADC at the back end. So, to cut a long story short, the signal processing equivalent of this animal is basically the equivalent of cascading 2 biquads and sampling the output and corrupting that sample with quantization noise, which is the quantization noise of the back-end ADC divided by the square of the gains that you have, because you have 2 stages. And because the noise of this stage is severely attenuated, the entire noise of the ADC is actually coming from only one stage, even though the filtering is happening in two stages. So that is the fundamental advantage of this, which allows you to break that fundamental power noise trade-off that's inherent in a standalone filter or a standalone ADC. So here, for example, remember, in our standalone filter, when we cascaded 3 identical sections to be able to get the sharp roll-off, each one of those filter sections was adding noise. And therefore, the noise spectral density at the output of the standalone filter is 3 times that of a single section. On the other hand, with a continuous time pipeline, you cascade 3 sections and you get the same sharp filter response, but the noise remains largely unchanged. So in other words, we are basically we are able to realize high order filtering without the accompanying noise penalty. So for the same performance, and you have 1/3 the noise, so that basically translates to a power advantage by a factor of 10. So to summarize, the power dissipation for a given noise in a standalone filter goes as the square of the order, and again that's nothing to do with bad design practice or to doubt the competence of the designer. This is a fundamental thing. In a similar way, the continuous time pipeline allows you to get sharp filtering with a noise which is independent of the order. Now, so this is the signal chain when you have, this is a prior art signal chain, which is what is used in practice. This is an ADC, this is a buffer, and this is the anti-alias filter. Now, when you have a continuous time pipeline, which is an ADC and a filter combined into one, the back-end ADC, as we saw, can be much simpler, and therefore its capacitance can be very small. Therefore, you can remove the buffer, and you have an anti-alias filter. And as we just saw, this equivalent anti-alias filter has got much lower noise. It also turns out that the linearity is much better than a standalone filter. And finally, because you're driving the filter, you're not driving these spikes of current, so these converters are very easy to drive. So in analog design, analog mixed signal design, people quantify their design space along 4 axes: power, area, noise, and distortion, right? And to be able to, if you want to reduce power dissipation and keep the same distortion, then you will end up paying a penalty in noise. As we discussed before, reducing power by a factor of 2 causes noise to go up by a factor of 2. Okay? If you want to, on the other hand, to keep the same noise in the area, but you want to keep the same noise as before, but you want to reduce distortion or to increase linearity, then it turns out that you'll have to burn more power because the amplifiers have to become more linear. So ideally, you would like to have a block which has no power, no area, no noise, and no distortion, right? Of course, that's not possible. So what you would do is try to minimize the area, so if you will, of the square, right? And for a standalone filter and an ADC, that's simply not possible, because if you try to reduce one, something else goes up. It's like a water bed, right? You go and stick your foot on one side, at some other place, the stuff will go up. But with a continuous time pipeline, it turns out, as we just saw, that you can reduce power, area, noise, and distortion all at the same time. So this is not, this is not merely, I change bias current by 2 microamperes and got like half a dB more distortion or less distortion, right? It's the continuous time pipeline is actually a fundamental improvement, which is brought about by combining filtering and A to D conversion in one block. So here, we built a converter in 65 nanometer CMOS with 100 megahertz bandwidth and 800 megahertz sampling rate. So you can see that the oversampling ratio is 4 in 65 nanometer CMOS. This is the chip. and it uses a 1.2 volt supply, and I'm not sure, people who have not measured ADCs or looked at ADCs before will be able to appreciate this, but the bottom line is that it works. And this is the frequency response of the equivalent filter. You get, it's a 3-stage continuous time pipeline. So basically, the equivalent of 100 megahertz 6th order Butterworth filter, and you can see that it rolls off at 36 dB per octave as advertised. And so because the continuous time pipeline is a filter and ADC pushed into one, you can compare it with prior art. You can either compare it with prior art ADCs or prior art filters. So if you want to compare it with ADCs, standalone ADCs, which have been reported in the literature for many, many years, you can think of this continuous time pipeline as an ADC which is preceded by a 0 power, 0 noise, 0 distortion filter. Of course, it's being very, very charitable to the ADC. And if you compare it with state of the art, you can see that it's comparable. But what really shows up is, you can also think of it as a filter followed by a 0 power, 0 noise, 0 distortion ADC. And there you can see that these are all logarithmic figures of merit, and you can see that as you would expect, you basically see order of magnitude improvement in power efficiency for the same performance. So to summarize, the continuous time pipeline is, rather than optimizing the filter separately and the ADC separately, which has been done for many decades, and as far as filters are concerned, it's very hard to get more than half a dB, 1 dB improvement by coming up with something clever, because you're up against thermodynamics. And whereas jointly optimizing the filter and the ADC together leads to orders of magnitude improvement than optimizing individual blocks. So it's a recent technique, and we've had a lot of fun with it. We've learned a lot. Of course, then it's also very industrially relevant because, as both Professor Bhaskar and Ashwin talked earlier, an analog to digital converter is like a processor, right? If you give a faster processor and more memory, you can be absolutely sure that software companies I will not name will come up with software which will fill up memory and the processor in no time, right? Likewise, if you give people a faster ADC, right, they will always find applications for it. Okay, so ADC therefore is enabling technology. If people figure out that you can make, I don't know, a 200-bit ADC, they will use it. Okay, so that's all I had to say. Before that, let me acknowledge my students. Sarvana is now an assistant professor at IIT Roorkee. Nishant and Chaitanya are PhD students who are working on this topic, and are collaborators from Analog Devices in Toronto. So thank you all for your time and attention, and I'm sorry I over.